Greetings. Today we're going to be discussing this concept of interest, which is the foundational concept in most financial situations. We reminded that interest is simply the cost of borrowing money or the cost to borrow money. There are all types of interest models that we may use that address certain financial situations. We have simple interest, and one we'll look at today is probably one of the most popular. And we'll call this compound interest. I'm sure you've heard of this before in life and maybe in a math class. And it's primarily evident when we talk about regular savings accounts, where we have a one-time deposit, and we kind of want to see how it grows over time. So in general, we're looking at certain accounts, maybe savings accounts, that if you leave money there, they will never lose money or lose value. The equation we normally use for compound interest looks as so, and we'll talk about each component of it and look at a problem as related to it. We have A equals P times R over C plus 1 raised to the C times T power. Now, this A here we refer to as the amount of money in the account after adding interest. Okay, so it's like that final account after a certain time where interest has been active or activated, how much money is in the account when it's all said and done. Okay, you may recall that P is called the principal or principal, and that's generally what we mean by the initial deposit. How much money was put into account initially. Yes. R here, we put this R here, is referred to as the interest rate R, and you can expect that it would generally be given as a percentage. We'll come back to that C there in a second, and the 1 is just the 1. This T here, of course, represents time, well, generally time of growth or growth time, and it's generally given in years, okay? Now, this value here, this C, which is the same thing as this C right here, we'll bring this over here. What we're going to do, we're going to call this the compounding period. Compounding period, okay? And it refers to the number of times that interest is compounded. I'm going to abbreviate here, compounded per 1 year. Okay, so we're going to have to take a look at a problem to kind of see how that is hashed out, but it's basically what's called the compounding period, the number of times that interest is compounded per 1 year. And although the problem may state that the money is in the account for more than 1 year, our C is just going to be based on the compounding period for just 1 year, just in general. Okay, so we want to remember this formula and see how we can solve different problems that relate to it. For example, this may look familiar if you saw the lecture on simple interest. In fact, it's the exact same problem except for some other part here. And so we say here, example 1, determine how much will be in Pam's account if she deposits $3,000 at an interest rate of 1.2%. Assume she leaves the money in the account for 2 years. Assume monthly compounding. So when we solve these problems, the challenge is to go from English to math. That's the idea. Can you start off with something in English, make the transition to a math formula, and then solve it and give an appropriate answer? Now, one of the things we have to remember when doing any of these problems is, first of all, make sure we're using the right formula. Now, how do we do this? Because there's another lecture that I have where I use the exact same problem and it has a different interest model. In this particular problem, notice here the certain buzz term, assume monthly compounding. So it's not simple interest, but it's monthly compounding. So something's happening every month. Something's happening every month. Okay, well, how much will be in Pam's account if she deposits? All right, well, we see different components of the problem here. Well, how about this? She deposits $3,000. Okay, so that sounds like P, the initial deposit. Our interest rate, if you observe here, is 1.2%. And our T, of course, is 2 years. She leaves the money in the account for 2 years. That was the interest rate right here. Now we look and see what else we have here. Determine how much would be in Pam's account. Okay, so futuristic kind of idea. How much will be in the account? So that sounds like A to me. How much will be in the account when it's all said and done? Remember, that's the A. Now there's one other value here that we have to think about. If you remember the equation that we looked at here, and that is the value of C. You see that C there? It's a compounding period, number of times that interest is compounded per year. So if we go back here, the clue is assume monthly compounding. Monthly. Well, we can figure out what our C value should be here based on that clue, monthly compounding. So we're going to ask ourselves, how many times is interest accruing within 1 year? Now, she leaves it in the account for 2 years, but when we come up with the value of C, we're going to only answer the question in terms of how much compounding that's given in a problem occurs in 1 year, and it turns out that it's going to be 12. Monthly compounding has an accompanying C value of 12. January, February, March, all the way to December. Within 1 year, that's 12 months, or our monthly compounding assumes that C is going to be 12. Within that 1 year span, interest would have compounded 12 times. Okay, so we take a look at the formula here. If I can sort of rewrite it here, R over C plus 1. Eventually you'll start to do this in your sleep. So we have A equals, now we start putting in the values that we have here. 3,000 is our P, times. Now when we put in the value of R, we have to change the the percent to a decimal. So we have 0.012. You're essentially moving the decimal twice to the left. Divided by, the C is 12. Okay, plus 1, I'm just writing the formula. You know, the plus 1 just comes down. Then times C, again, which is 12, times, and how long do we have it in there? For 2 years. Okay, and as a general rule, you can put the parentheses around that entire exponent so that you're not confused. Now, this is the most basic type of a problem that one can use to solve this. You can put it, depending on what kind of calculator you have, you literally can put this entire string of function in the equation in your calculator, and you should be able to get an answer. In particular, you have to remember order of operations, right? We do this part first. Then once you get that answer, you raise it to this. And then after it's all said and done, then you multiply by this thing right here. Okay. Now I have a calculator here kind of ready to demonstrate, and you can literally just put the equation inside of here. So let's try to do it. I'm going to say 3,000. Any really good calculator knows order of operation times 0.012 divided by 12 plus 1, close parentheses. Now, you have to know what raising to a power is. In this particular calculator, this is calculator.net. You raise it to the power of, but you have to be really, really careful. As I mentioned before, I'm putting a new set of parentheses in the exponent, 12 times 2, then close parentheses. So if you have a really good scientific calculator, it should be able to give you the right answer out of there. So you can look at that string, or you can sort of do it by hand and do part by part by part. And you find out here that you see the answer right here, 3,072.834. Notice when we do it this way, we don't round too early, right? You want to try to keep as many decimals as possible until you get your final answer, and keep maybe two decimal places afterwards, since we're talking about money, right? So it's like 83 cents. So it's looking like the final answer it's looking like here, let's see if I can get this here correctly. $3,072.83 is our final answer. Okay, so again, this is a more standard, typical, easier type of problem because you're trying to solve for A. So all the action is occurring on the right side of the equal sign. So you can literally put that equation in a calculator, or if you're not really comfortable with that, just go bit by bit. But just remember order of operations, as I mentioned before, you've got to do parentheses first, then find that answer, then raise it to the 24th power, as it were, 12 times 2. Then after you get that answer, then multiply by 3,000, and you should get this right here. If you watch my other lecture, I do the same problem using simple interest, and it comes out that in that case it was 3,072. So we just add on the extra 83 cents when we use compound interest. You typically make more money in accounts that have compound interest versus simple interest. And this is just an example of a Mickey Mouse example to kind of show you how you have the same exact numbers for P, R, T, and we just added on that C equals 12, which has the influence or impact of adding on this extra 83 cents eventually. So continue to work with the problems. This is the most basic when we deal with compound interest. We're going to look at other lectures where it may not be as simple if you use a compound interest problem, depending on which variable you're trying to find. Okay.